Now, let's look at this second one. Now, after the first equation, we know a lot of things that we see here, right? We
So
know what
this is
this is.
for H.
So the magnetic field. Okay, so H here, when we talk H, we're talking about magnetic field. Now, in SI units, generally it's with ampere per meter, correct?
Yeah.
Yes. Amperes per meter. Del dot we already know.
Yes.
Right? Now, we also have this here, mu.
Mu.
Mu is what we call
Permeability.
Yes. Call it magnetic permeability. H we know.
Yeah.
Is equal to 0.
Yeah. So nothing diverges from closed.
So that's interesting
volume.
because
Yeah.
you said in the electric field case, you need to have equal number of positive and negative charges
For this to happen.
For this to happen.
Yeah.
But in this case, what you're saying is the divergence of H, which is how much H changes.
That means the amount of field that's going out and that's coming back to that volume is equal.
Yes. So let's look at the picture we drew before, right?
Yeah.
We had, let's say, we take positive just in case.
But these are not charges.
Sorry?
These positives are not charges.
Maybe you're like the smart kid in the class who, before the teacher is saying, I know the answer to this. But you're right. You're right. So you're getting there, right? So now imagine this kind of 3D structure object. Now, instead of charges, let's say this has some magnetic field here.
Okay.
Let's say inside there's a magnetic field.
Okay. So you are comparing electric field and magnetic field.
Yes.
So that's why I got confused.
So yeah, you have something like this.
Yes.
No, I'm sure. Sorry, this is the surface we're talking about.
Yeah.
Okay. And let's say it's a closed surface. What can you see from here compared to this? What's the first thing you see here?
So the second one is a closed loop.
Yeah. So this is electric fields, right?
Yeah.
And this is we're talking about
Magnetic fields. So magnetic field lines are continuous, closed. The other one starts from somewhere and ends.
Diverge. But here, whatever is started here goes back into that closed surface.
Yeah.
So the net is
So the divergence will be 0.
0.
Oh, that is what this equation says.
Yes.
Oh, okay.
Nothing coming out because what goes out comes back in, right? So it's 0, no matter how many flux lines you have, right? And also, this is the reason why there are no monopoles of magnets, right? You can get a magnet, you can cut it into the smallest peaks, you can still have a north and south.
Yeah.
Right? So compared to electric field, this is the major change.
That's the beauty of it.
Yes. That's the beauty of it, yes.
Mu is similar to...
Sorry, yes. You like this constants, Bobby, don't you? Now, we talked about electrical permittivity. Now, this mu, which is magnetic permeability, okay.
Yeah.
Is the response of a material to a magnetic field. Right? Before it was response to an electric field, now response to a magnetic field. But there's a little difference here.
Hmm.
Okay, so now before we talked about kind of atoms reorienting themselves, right? Now let's say if you look at a magnetic material, and let's say this is a certain magnetic material.
Soft iron?
That's it, for example. Or let's look at a material that has random, that has domains in random directions.
Yeah.
Okay. So these have what we call domains. Okay. And generally, when there's no external magnetic field, they might just be on their border, right? I mean, I have it in one direction, but it's in both directions, right? Now, what happens when you apply, let's say, a magnetic and external magnetic field in this direction? What's going to happen to these domains?
Maybe some of them will get aligned.
Yes. So again, depending on the material, right? If its response to an applied field is high, you'll see that most of these will align in the direction of the magnetic field.
Okay.
Right? But if not, as you said, only some of them will align.
So that feature is captured in this.
Yes. So what that means is mu. It's captured in this magnetic permeability, right? So the higher the mu is generally, right, the more responsive it will be to a magnetic field, right? But divergence of that still is zero. Okay. So
so like electric field, we said electric flux density B equal to epsilon E. Like that, is there something equivalent here?
Yes. So here, let me. So I think last time we had our closed surface. And then we said, okay, there's, let's say, some virtual magnet here. That is basically near this magnetic field. Yeah. So coming out. Then if you take a very small area again here. Okay. Let's say there's also field coming out there. Okay. And let's say this is B.
Okay. B is?
So H is the magnetic field. P is what we call the magnetic flux density.
Okay.
Okay.
So equivalent to that D.
Yes. So B is the
electric flux density.
Yes.
Sorry. Magnetic flux density
is the amount of field lines coming out of a surface. Right? So
in a unit area.
In a unit area, right? The amount of field lines in that unit area is called the flux density, the density of lights coming out.
It's what is a like B, the field lines or flux lines?
Yeah.
We use another term, phi, I think. Flux.
Magnetic flux. Yes, that is flux. This
is
flux.
Phi per unit area or phi per area.
Phi per area
is B.
Is B. Yes. So this is your flux. This is the area.
Yeah.
Right. Which is, let's say this.
Yeah. So what you're drawn is flux.
Yes. What I've drawn is, if I take a certain area, that's the what I've drawn is a flux. But if you take the area, it's the density of flux coming out of that area.
Yeah.
Correct. So again, we do a very similar thing here. B is coming out. Right. You have again a normal component.
Yeah.
Right.
So you will take the
cos
projection on that
Yes. Okay. So again, for the magnetic flux density, we take a projection of that onto the end. So again, it will be something like P n cos theta. Sorry, by cos theta. The amount of flux coming out of that. Okay. So
Should we give some value for the air, the mu?
again,
mu 0.
correct. So you talked about E0, right?
Yeah.
Similarly, here you have this for air.
Yeah.
And similarly, here you have mu 0 for air.
Yeah.
You know the number, please.
That is easy to remember. 4 pi into 10 power minus 7.
4 pi
into 10 power minus 7. Henry per meter, I think.
Henry per meter. Right? So, you can see a lot of analogous.
Yeah. Between these.
Between, analogy, yeah. Between these two. So, again, you talked about mu for different materials, right?
So, equivalent to epsilon R, there is something called mu R.
Yes.
Relative permeability.
Which is
Permeability.
divided by mu 0.
Yeah.
You know any materials that has...
Yeah, I know, but exact value will be difficult. See, for example, this transformers are made of transformer sheets, no?
Yeah.
I think that's a silicon steel. It's about 1,000, 1,300.
Mu R is 1,000.
Yeah.
What about water?
Water is like...
very low.
It's like air.
So this is a good point, right? Because that's why certain materials, right? If you want to, let's say, work with water, maybe magnetic fields are not the best option.
Yeah.
Right? Maybe it's better to use electric fields.
That's correct.
Right? Which is why we have separating
very correct
magnetic field to electric field. Yes. So you said like mu R for let's say
silicon steel.
Silicon steel is about 1,300.
Yeah.
About that. So that's
approximately.
Yeah. So just to give you an idea.
But you can get materials with mu R of 1 lakh.
1 lakh?
Yeah, 50,000.
But not naturally occurring like this. You have some
alloys, yeah. It's something called mu metal.
Mu metal. I've heard of mu metal.
Yeah.
I've heard of mu metal. 1 lakh. So what kind of applications? Maybe space applications or something?
Even for sensors it is used. And even some kind of special current sensors.
Oh, that's very large. Yeah. I've come across like nickel.
No, there are composite cores of similar range. Mu R of very large.
But 1 lakh, I don't think. No, even nickel or neodymium or any of that.
Yeah.
I don't think they reach 1 lakh.
Yeah. I think permalloy also very large value. There are various materials available, but mu metal, permalloy, etc. are well known.
Right. So just for comparison, you said mu R of silicon steel is 1,300. Then mu R of air is very close to 1.
Yeah.
Right? Similarly, I think if you look at the electrical permittivity of this material, maybe it is quite low.
Yeah, it's there it may not be applicable because this material also may be conductive.
So there could be some.
Yeah.
Right. So there could be materials that has a.
So mostly this epsilon R, we were talking for materials that are insulators.
So, right.
Correct.
Yes. I mean, that has a large value is. But basically insulators.
Yeah.
So there are materials then that has both a high permittivity and a magnetic commutability, I guess.
Could be. Yeah.
Okay. So then, in summary, the total magnetic flux passing through any closed surface is 0. Yep. Divergence of the magnetic field at any point is also 0. Magnetic flux lines always close upon themselves. You saw that before. Oh, that's just
Yeah.
repeating.
And D, we said it is epsilon E.
D is epsilon E.
Similarly, B is mu H.
Good point. Yeah, let's make a bit here. So yes, so we said D, which is electric flux.
Yeah, electric flux density.
Electric flux density is this. Okay, and then similarly B is 0.
Yeah. Or it need not be mu 0, mu H and epsilon E.
Yeah. I mean, yes.
Yeah, this is only for
Yes, that's correct. Yes.
This will also be useful when we design something.
Later on, we will see how these values come into the picture. Okay, so that's the second law. All right. So far we're talking about static fields. Static electric fields, static magnetic fields.